Alright, let's go. Another video. Carboxylic acids and their derivatives. So I'm going to look at all the carboxylic acids and their derivatives in one go. So this one video might be a little bit longer than some of the other ones. Right, cut to the chase. Here we go. Functional group, carboxylic acids, and an example of nomenclature. So I'm going to have a go at doing this. So here we go. I'm going to say, what is a carboxylic functional group? And I think it is C double bond O with an OH. I'm going to draw the simplest one I can. So it's one carbon, so it is meth. And how would I name it? Anoic acid. Sweet. Alright, so I could have ethanoic acid and propanoic acid, and then I could have other stuff on the end of it, couldn't I? So I could have, alright, let's see what we could have. OOH. Let's make this all nice little kind of, yeah, semi-ish. That's 1, 2, 3, and we have a CH3 up here. And give me CH3 too. Haha. Right, so meth-eth-prop, we should start from here. Meth-eth-propanoic acid with 1,2-methyl, 2-methyl-propanoic acid. Do I have to have a number for the anoic acid? No, because it's always at the end of the chain. Sweet, right, easy, done. Back to this. Just a few little things about carboxylic acid. So you've got to remember acids taste sour, so you think about ethanol in wine. When it's oxidized to ethanoic acid, it forms vinegar. Would you rather drink wine or would you rather drink vinegar for taste? Wine, because vinegar tastes sour. When you suck on a lemon, okay, that part of that kind of sour taste is due to the citric acid, which is a sour tasting carboxylic acid. Okay, organic acids are weak acids. The smaller molecules dissolve in water and react by donating a proton to the water. This means aqueous solutions turn litmus pink. Now let's just delve into that temporarily here, since we have the technology to do this. What that means is, if I had, use my favourite example here, right, ethanoic acid, right? If I have this as an aqueous solution and I have it in water, right, this is a equilibrium acid, it's a weak acid. This means it is equilibrium, so we draw an equilibrium arrow. It goes this way and this way, reaction goes both ways. I'll have CH3 COO minus aqueous and H3O plus aqueous. Now this is considered to be an equilibrium that lies mainly to the left. Okay, most of my stuff is here, a little bit of my stuff is here, but enough of the stuff is this way that it is considered, it should be pink, so I should read. It is considered to be hanging out with enough of the H3O plus being created that it is an acid. So this here, this ethanoic acid, donates a proton to the water. The water accepts that proton. This is a Lewis acid, Lewis base. This is the conjugate base for the acid. This is the conjugate acid for the base. Okay, so yeah, acidic. Easy? I hope so. Right, moving on. Oh look, I dread it down there anyway. Right, a little aside though, this here is called an ethanoate ion. Okay, so ethanoic acid, ethanoate ion. If I had methanoic acid, it would be methanoate ion. Propanoic acid, propanoate ion. Alright, we'll go on to that. Here we go, salts. So the anion formed when a proton is donated to water, or hydroxide, has the name ending OH. For example, ethanoic acid reacts with sodium hydroxide to form my favourite, sodium ethanoate, CHA-CU-NA. I hope you're singing along in my head. Alright, and propanoic acid forms sodium propanoate. Alright, cool. Oop, too fast. The salts of carboxylic acid, such as sodium ethanoate, are basic when they dissolve in water. The conjugate base of the weak acid reacts to a small extent to form the carboxylic acid and OH minus. Right, now what the hell do I mean by that? Let's show you. So salts of carboxylic acid such as sodium ethanoate. So I have this thing to start with, CH3COO Na, dissolve in water, alright, to form the conjugate base of the weak acid, CH3COO. Ooh, I know what I've done here, it's alright. This would be COOH plus OH minus plus Na plus, because this comes off, right? And I'll have this reacting with the minus to make this one, which is aqueous, and this one here is aqueous, and this one here is aqueous, and this one here is liquid, and this one here is aqueous. Cool. Alright, so I have this reacting with water and makes OH minus, which makes this basic solution. Right, again, this is an equilibrium, and this equilibrium runs mainly to the left. Just keeping that in mind for later on when we do equilibrium stuff. Cool. Alright, carboxylic acids can be reduced to their equivalent aldehydes and then to their primary alcohols by using the reducing agent sodium borohydride, same as we talked about in the previous ones. We're talking about aldehydes and ketones. Cool. Right, so substitution reactions of carboxylic acids. Now, carboxylic acids can undergo a number of reactions. Okay, so we can substitute the OH of the COOH. Okay, so that C double bond O stays, but the OH we can substitute. So we can make acid chlorides, we can make esters, or we can make amides. Right, so let me just draw a couple of those out just so you kind of get the gist. For those of you who don't like this kind of notation, this would be, instead of carboxylic acids, RC double bond OOH. Right, that's the acid. Acid chlorides would be RC double bond OCl. Esters would be C double bond O from the carboxylic acid, and then O R dash from that alcohol, and amides would be C double bond O NH2. Cool. Again, I remember amides, not amines. Amides are the acid derivative of, yeah, with the a kind of thing on the end. Yep. Alright, here we go. Esters. So using alcohols and an acid catalyst such as concentrated H2SO4, carboxylic acids undergo a substitution reaction to form esters. No, I didn't have that there. Right. Quickly, Mrs. A. So if I had C double bond O, OH, if I had methanoic acid and I had let's draw it around this way, CH2 CH3 ethanol. Alright, then this would react under an acid catalyst, concentrated H2SO4 and heat. Okay, this will make H C double bond O O CH2 CH3. Okay, now let me just change colour so you can see this bit here and this bit here will be the bits that are taken away. This oxygen here, right, comes in and attaches itself onto here. So this is substituting this OH group for the rest of the alcohol. So I'd have H plus H2O. Okay, it's also called a condensation reaction because little molecule was being released. And what else was I about to say? I was about to say that the name for this one would be, we name these the alcohol section first, so this will be ethyl methanoate. Okay, this bit first, then this bit, the bit with the single bond O. Oh, the single ladies. Oh, the single ladies. Comes first, and then the C double bond O comes second. Sweet. Acid chlorides, ROCOCl. These are way more reactive than carboxylic acids themselves, and they react vigorously in water. They actually spit and fume, and just quite nasty. If anyone can find me a decent video of that, I'd be quite keen to watch one. Feel free to post it for us. So this reaction happens with one of the 3 chlorinating agents. So we have, again, C double bond O. Let's say we'll have methanoic acid again. So this can be PCl3, PCl5, or SOCl2. So either that or that or that. Alright, we'll end up making HC double bond O, Cl, generally plus HCl, maybe some SO2 depending on what you've got, or this is on page 147 by the way, if you want to know exactly what it all makes. But it definitely gets rid of this, and so it's just that on there, and put Cl on there. Oh, sorry, yeah. Alright, cool. Oh, haha, check me out. This is the opposite, how they react vigorously in water. So when you add the acid chloride into water, you will make carboxylic acid, NaCl, spits, fuming, highly exothermic, quite fun to watch, not fun to do. Acid chlorides are more easily converted to esters and amides than carboxylic acids are. So if you have a reaction and you want it to go efficiently, you would use an acid chloride. Alright, so there we go. There's a couple of examples of making esters and amides from this. Right, there we go. Brilliant. Substitution reaction. Last one, amides. Amides are solids. They have no smell, and aqueous solutions are neutral. They are not basic. Remember that the only basic organic molecule you come across in this course is amines, nothing else. Okay, so you name them nomenclature by changing the N to amide instead of the E on the end. They can also be formed by substitution reaction of acid derivatives. So you can have an acid chloride and ammonia going to the amide and HCl. This one is preferable because it's really fast and really easy, as opposed to an ester and ammonia. You have to heat the crap out of it, and then you make amide and alcohols, and it's really slow. Right, and you can make it from acids, but you have to go through 2 steps. You have to use ammonia, which is a base. So the base attacks the acid, base, acid, right? You make a salt. Acid and base is salt and water, yeah? We know that. Okay, the salt you then have to heat up to make the amide. Okay, to decomposes, we say. So, not the easiest way to make it, but it is plausible. Acid and base. Sweet. Alright, so here's some questions for you. What I suggest you do is you pause the video now, because I believe I have the answers after this equation. So, equations show the structural formulae of the reactants and the products in the following substitution reactions. So I've got an acid chloride and ammonia, which was just on the last slide, and methyl propanoate and ammonia, heating required, which is again on the last slide. Have a go, and we'll come back in 10 seconds. Or not. There we go. Faster. Alright, so there's the answers. Hope you had those. And last little bit of this is amino acids. Amine group, acid group. You must have heard of these things before, hopefully. If you've done bio, for sure you will have. So amino acid, here's a glycine one, and here is alanine. So glycine is one of the simplest ones you can have, just H's. Alanine is the second easiest one, because instead of the R group being down the bottom, it's just being H. We just put a methyl group there. Yeah, pretty easy to name. Amino acids both have a basic group and an acidic group. In acidic solutions, the basic NH2 group is protonated and forms a positive amino acid. In alkaline solution, the opposite happens and you get negative ions. What happens is that you can actually get a Zwitter ion, which is this fantastic thing here, where you have a positive thing and a negative thing going on the same dealio, and that's about us. Alright, I'll see you again for the next one.